Tonight, you're here with me on the Sleepy Story Facts channel, and we're stepping into a gentle nighttime story made of stone, time, and quiet chain, the kind of relaxing story that makes it easier to fall asleep and drift toward deep sleep without effort. So get comfortable, let your shoulders soften, let your jaw unclench, and allow your breathing to slow, as if the whole day is quietly setting down its weight beside you. In this calm bedtime story, we're not rushing anywhere. We're simply listening to the earth the way you might listen to distant rain. Because long before maps, before names, before the first person ever looked up and wondered at the stars, the planet was already moving in its own patient way, shaping and reshaping itself without needing an audience, lifting rock, wearing it down, opening seas, closing them again, turning heat into land and land into sand. And even now, beneath every home and every street and every forest path, the ground is not a fixed thing, but a slow, steady conversation between pressure and time. Geology, in its softest form, is the story of the earth remembering itself, written not with ink, but with layers, crystals, and the quiet signatures of fire and water. And as you listen, you might imagine that every pebble holds a small secret, that every cliff is a long sentence, and that every grain of sand is the end of a chapter that took millions of years to finish. And if you ever want to return to a calming narration like this, a gentle bedtime story for adults, you can always come back on another quiet evening. But for now, there's nothing to do except rest and let the ancient world carry your thoughts like a slow, warm tide. To begin, consider something surprisingly tender about our home planet. The crust, the solid skin we live on, is much thinner than most people expect. And if the earth were shrunk down to the size of an apple, that crust would be like the apple's peel, a delicate outer layer wrapped around something vast, heavy, and hot. Beneath the continents, that layer might average around 30 km thick, and beneath the oceans, it can be closer to 10 km. And when you hold those numbers in your mind, they start to feel almost like a whisper compared to the size of the whole world. Under that thin shell lies the mantle, a region so enormous it makes up most of Earth's volume. And although it is made of rock, the heat and pressure down there allow it to move with an unhurried, syrup-like patience, not fast like water, not sharp like wind, but slow like honey in cool air. And this is why the crust can ride above it, floating the way broad, stiff rafts float on a deep hidden sea. From far away, mountains and valleys might look dramatic, but at the scale of the planet, they are small ripples, gentle textures on the surface of a great stone sphere. And it's calming to realize that your entire life happens on this slender outer layer, a thin, safe place to stand, while the deeper earth continues its quiet work below. And when we look at familiar rocks, the feeling of deep time becomes even softer and more real, because some stones we touch today were once flowing heat. Granite, for example, seems sturdy and settled, speckled and cool, the kind of rock you might see in a countertop or a mountainside. Yet it began as molten material gathered far beneath the surface, in slow chambers of magma that pooled and shifted like underground rivers of fire. There, over immense stretches of time, the melt cooled so gradually that crystals had the chance to grow, forming grains of quartz and feldspar that locked together like a calm mosaic. And what you see now as solid granite is the quiet ending of that long cooling, the final stillness after an ancient glow. When your fingers brush granite, you're touching a memory of heat that took its time becoming stable. And in many places around the world, great landscapes owe their shape to these deep intrusions of magma that never erupted, but instead rose and hardened underground, later revealed as softer layers above them wore away. It's a soothing thought, really, that solidity can be a slow achievement, that what feels permanent is often just time taking a warm, patient breath and then settling. And then there are diamonds, which hold a different kind of calm wonder, because they begin as ordinary carbon, transformed by conditions so intense they feel almost unreal. Many diamonds spend astonishing spans of time deep within the mantle, where pressure presses atoms close and heat encourages them to rearrange into a tight, bright structure. But the Earth doesn't always work at one speed, and under certain extreme conditions, carbon can shift into diamond very quickly, almost like a sudden click into place. Either way, the setting is far below, in darkness and heat, in pressures that are difficult to imagine clearly. And when diamonds reach the surface, it is usually because volcanic forces carried them upward through narrow pathways of rock, lifting them from deep earth toward open air. Each small crystal is like a quiet record of transformation, a reminder that change can be both slow and sudden, that the planet holds many tempos at once, and that beauty sometimes forms where no light reaches, only to rise much later into view. And now, as the night grows softer around you, let your mind rest on another gentle truth. Some mountains are still being lifted, even now. While you listen, mountains look timeless, like they have always been there and always will be. But they are part of a living cycle, shaped by plates of crust that press and fold and slowly push rock upward. And in places like the Himalayas or parts of the Andes, uplift can continue at a pace that, in its own quiet way, competes with the steady growth of your fingernails. At the same time, wind and rain and ice patiently wear those heights down, grain by grain. And so the landscape becomes a balance between building and dissolving, between rising and smoothing, a rhythm that has been repeating for hundreds of millions of years. If time were sped up like a film, a mountain would seem to inhale and exhale, swelling upward with collision, then softening under erosion. And it's peaceful to imagine that rocks beneath your feet may once have rested on an ancient seafloor, later carried upward until they met the sky, not with drama, but with steady insistence. And all of this becomes easier to picture when you remember that continents themselves are travelers, drifting across the planet's surface in movements too slow for a single human life to notice. The mantle beneath the crust is hot enough that solid rock can slowly flow. And on that slow-moving foundation, the plates of the crust slide a few centimeters each year, separating, meeting, and gliding past one another. And while those distances seem tiny, over millions of years, they redraw the map of the world. Oceans can open where plates pull apart, and mountain ranges can rise where plates press together. And climates can change as land masses shift toward warmer or cooler latitudes. And long ago, These movements gathered the land into a supercontinent, only to pull it apart again, like a very slow tide rearranging stones along a shore. In this bedtime story, it can be comforting to think of yourself as a quiet passenger on a steady raft of rock, carried gently through geological time without ever feeling the motion, safe and supported, while the planet does its careful work. And perhaps the most soothing idea of all is that the surface of Earth is not a finished sculpture, but a renewing one, because plate tectonics continually recycles the crust, making and unmaking the ground in a long, restful loop. Where plates meet, rock can crumple and rise into mountains, and where they separate, molten material can rise, cool, and form new ocean floor, spreading outward in slow symmetry. Elsewhere, one plate can slide beneath another and sink back toward the mantle, returning surface rock to deeper heat, melting and blending into the planet again. And even the seafloor, which feels so ancient and unknown, can be created and replaced on the scale of tens of millions of years. Every cliff, every beach, every volcanic plain, every rounded pebble is part of this ongoing exchange between surface and depth. And as you relax into the gentle bedtime mood of this sleep story, you can let that thought settle in. The Earth is quietly active, continuously renewing itself. And in that steady cycle, there is a deep kind of comfort, like the feeling of a slow heartbeat in the dark. As you continue to rest with this gentle bedtime story, you can imagine the Earth beneath you like a living, quiet skin, never quite frozen in place, always renewing itself in slow, graceful motion. And in this calming narration, we're simply watching that motion with soft attention, the way you might watch shadows move across a wall at night, high above, where air grows thin and clouds drift like pale scarves. The Himalayas are still rising, not as a sudden leap, but as a steady, almost tender lift that began tens of millions of years ago when the Indian plate pressed into the Eurasian plate, and the crust folded and thickened the way fabric gathers when your hands gently push it together. That meeting did not end. It continues, and the mountains respond with patient growth, measured in small amounts each year, while wind and ice work in the opposite direction, smoothing and carving, turning sharp stone into softer shapes. So the range becomes a balance between uplift and erosion, building and wearing. And even the earthquakes deep below can be understood as quiet signals of pressure, still finding its path through rock. As the collision continues, it can be soothing to remember that these peaks are not just ancient monuments, but ongoing creations, still being shaped under the same slow forces that once raised their earliest ridges. And while people live their entire lives without seeing a summit visibly change, the planet never stops its careful work, reshaping the ground beneath millions of sleeping homes. And when you widen your imagination from mountains to whole continents, the movement becomes even more dreamlike, because the lands you know are drifting at rates so small they feel like nothing. And yet, they add up over time until coastlines and oceans and climates are gently rewritten. Continents slide over the mantle, carried by deep convection, and over long stretches the Atlantic can slowly widen, while other ocean basins are gradually consumed, not with haste, But with the steady pace of a world that has all the time it needs over millions of years, the map would become unfamiliar. And this drifting helps explain why certain fossils and rock layers seem to echo each other across oceans, as if the Earth once held those distant places closer together, then quietly separated them again beneath the ocean. This sense of renewal becomes even more striking because the seafloor is, in many places, younger than the continents, continually created and carried away in a slow cycle along long underwater ridges. Molten rock rises, cools, and forms new ocean crust that spreads outward on both sides. And eventually, far away at deep trenches, older seafloor can sink back down toward the mantle, returning to heat, so that most oceanic crust does not survive beyond roughly 200 million years. A brief moment compared with the oldest continental rocks that have endured far longer. If you could watch the ocean basins across deep time, you might see them appear and fade like a slow breath, opening, widening, narrowing, and then slipping away, while the planet keeps making new seafloor in a rhythm as steady as a heartbeat. And hidden in that young seafloor is one of the most delicate kinds of evidence the Earth can offer. A pattern that looks almost like a quiet barcode stretched across the ocean bottom, formed by magnetic stripes that record times when Earth's magnetic field reversed as new lava cools at mid-ocean ridges. Tiny magnetic minerals align themselves with the magnetic field of that moment. And when the rock hardens, the direction is locked in place, so that later reversals create alternating bands of different magnetic orientation, laid down in parallel as the seafloor spreads. By tracing these stripes, scientists have been able to match the ocean floor's pattern to the history of magnetic reversals. And this matching became one of the clearest supports for the idea of seafloor spreading and plate tectonics, like a quiet signature written by magnetism, heat, and time. In a calm way, it's comforting to think that rocks can carry memories so precisely, because volcanic rocks can become natural magnets as they cool, preserving the direction of the field at the moment they solidified, as if each flow of lava took a small compass reading and then fell asleep in that position forever. And deeper still, beneath the sleeping surface of volcanoes, there are hidden chambers of molten rock, places where magma can gather and change slowly, forming crystals, collecting gases, and building pressure, until sometimes it finds a path upward through cracks and vents, reminding us that a volcano is not just a mountain, but a connection to a warmer world below. And not every eruption is quick, because some outpourings of lava can be vast and prolonged, covering large regions over long spans of time, laying down thick sequences of basalt again and again, until the landscape becomes a broad, dark plain of cooled fire. Proof that even eruption can have its own slow, patient version of time. And as you keep sinking into this soft sleep story, you can hold a gentle image in your mind of those ancient lava plains we mentioned, now cooled and quiet beneath open skies, once formed by long, persistent outpourings of basaltic fire that could continue again and again over long spans of time, releasing heat and gases that could influence climate, and in some eras, nudge life onto new paths. And if you stood on such a dark, stony plain today, it might feel peaceful and still, even though it was born from a slow, unstoppable spreading of molten rock that didn't need a single dramatic explosion to change the face of a region. And now, with that calm sense of time, let your imagination drift down beneath the waves, because most of the ocean floor is made from basalt, a dense, dark volcanic rock that forms from mantle-derived magma and becomes the broad foundation of ocean basins. Like a quiet armor laid down in heavy sheets, basalt is richer in iron and magnesium than many lighter continental rocks, which helps give it that deeper color and weight. And as new crust forms near mid-ocean ridges, it spreads outward, while older seafloor can eventually sink back down at subduction zones. So the ocean's stony floor is continually renewed in a patient cycle of making and returning. In this relaxing bedtime story, it can feel comforting to picture the seafloor not as something dead and forgotten, but as layer upon layer of cooled lava, quietly recording the slowest motions of our planet, built without hurry, altered without noise, over and over again. And sometimes the ocean shows us the most tender kind of volcanic artistry, because when basaltic lava erupts underwater, it cools so fast that it forms rounded, pillow-like shapes as the outer surface chills into a skin, while the hotter lava inside pushes forward and breaks through to form another bulge, then another, creating piles of smooth stone that look like stacked underwater cushions or balloons. These formations, known as pillow lavas, are strongly associated with underwater eruptions. And when people find ancient pillow basalts on land, they can be a clue that the area once lay beneath the sea, back when water closed over it like a dark, quiet blanket. It's a gentle thought that even in cold, crushing depths, the earth can shape its fire into soft curves, turning motion into sculpture in the space of moments, then letting it rest for ages. And another quick change rock is obsidian, a volcanic glass that forms when lava cools so rapidly that crystals don't have time to grow, leaving a smooth, glassy stone that can look black as night and shine like still water. Obsidian is famous for breaking with curved, shell-like surfaces called conchoidal fractures, and those breaks can create edges so sharp that people in many cultures valued obsidian for tools and cutting blades long before metal was common. A quiet meeting of geology and human history in a soothing way. Obsidian is like a paused moment, heat caught mid-motion, fragile in the hand, yet carrying the calm, glossy surface of something that once flowed, and then suddenly became still. And if you want an even softer kind of time capsule, there are rocks that can hold tiny trapped pockets, little bubbles sealed within, preserving chemical clues from the moment they formed, so that by studying them, scientists can learn about ancient conditions, like a whisper from an earlier sky, held safely inside stone for a very long time. And while your body grows heavier with sleep, you might also like knowing that some of the biggest mountain systems on Earth are not the ones you see from land at all, because mid-ocean ridges form long underwater mountain chains where new crust is created, stretching across ocean basins in the darkness, rising from the seafloor like an endless hidden backbone. And in that same deep world, the planet's lowest known point sits in the Mariana Trench, where the Challenger Deep reaches a maximum known depth around 10,984 meters, close to 6.8 miles, a distance that feels almost like turning the sky upside down and measuring it downward into the sea. It's often said that if Everest were placed there, its peak would still be underwater, which helps the mind gently sense how vast the ocean's hidden spaces really are. The trench is also part of the planet's renewing system, a place where one plate sinks beneath another in a subduction zone, returning surface rock toward deeper heat. Continuing the slow cycle, we keep meeting again and again in this nighttime story, and even when the world around you feels completely still, there is a quiet truth that the Earth is always releasing and adjusting stress in small ways, and sensitive instruments can detect countless tiny tremors that most people never notice, like a soft background hum beneath the day, reminding us that the planet is living motion, steady, subtle, and unbroken, while you rest and let yourself drift toward deeper and deeper sleep. As you rest into this nighttime story, it can feel comforting to remember that the stillness you see is only the surface of things, because beneath mountains, forests, and oceans, the planet is always adjusting in tiny, quiet ways, settling and shifting with slow rhythms that never really stop. And when you listen for it in your imagination, that hidden motion can feel less like danger and more like a calm, steady pulse. Sometimes, when a very large earthquake reshapes the land quickly, it can even alter the path of water. And in rare moments, rivers have been reported to briefly flow the wrong way as the ground lifts, drops, tilts, or forms temporary natural dams, reminding us that landscapes are not fixed stage sets, but flexible terrain that can be rearranged when deep forces move the surface. Yet not all movement arrives with a jolt, because some faults slide so gently that there is little or no noticeable shaking at all. A behavior known as fault creep or aseismic creep, where measurable displacement happens along a fault without the kind of earthquake most people would feel. The San Andreas Fault has a well-known creeping section, and USGS descriptions note that creep can occur with small earthquakes or without any associated large earthquakes, releasing motion in a quieter, steadier way than a sudden rupture. In this bedtime story mood, it's soothing to picture the crust not as a rigid shell that only breaks, but as something that can also glide millimeter by millimeter, like a slow exhale, easing strain here while transferring it there in the endless balancing act of tectonics. And if your mind drifts deeper, past the crust, past the mantle, toward the heart of the planet, you can imagine an inner world of metal and heat, where motion is not seen, but profoundly felt through its effects. Because the churning of Earth's core is tied to the magnetic field that surrounds our planet, stretching far into space like an invisible shelter. That magnetic field, the same one recorded in ocean floor stripes and in cooling lavas, is a reminder that the Earth's interior is active, turning and flowing in ways we can't witness directly, yet can gently trace through its quiet signatures at the surface. And in the mantle above the core, there may be another kind of secret, one that sounds almost like a dream. A vast amount of water stored not as an underground sea you could swim through, but as hydrogen and oxygen bound within minerals, especially in the mantle transition zone, where ringwoodite can hold water as hydroxide within its crystal structure. Research discussions of ringwoodite and the deep water cycle describe estimates ranging from about 1 to several times the amount of water in Earth's oceans potentially stored in the mantle, held safely inside rock over immense spans of time, cycling downward with subducting plates and returning upward through melting and volcanism. It's a soft, reassuring thought that even water, so gentle on the surface, has a deep, patient pathway through the planet, enduring in hidden places while the world above changes its seasons. And speaking of patience, there are places where time builds beauty so slowly it almost feels unreal, like the Cave of the Crystals in Naka, Mexico. Known for its enormous gypsum crystals that grew under stable conditions over very long periods, becoming towering, translucent forms that look like frozen light in the dark. And then, in another kind of slow miracle, salt itself can move like a thick fluid when buried and stressed, creeping upward through denser rocks in a process called diapirism, forming salt domes that bend and break layers above them as they rise over millions of years. Salt domes matter not only as geological sculptures, but also because they can create traps that accumulate oil and gas, shaping where resources are found, all because a solid material can behave with surprising softness when time and pressure are abundant. And now, still wrapped in this calming bedtime story tone, you can picture those salt domes once more, because from far above they can look like gentle swells in the land. Yet, beneath the surface, they are slow, powerful columns of salt that have been creeping upward for ages, rising because salt can behave like a very viscous fluid under pressure, bending and deforming as it pushes through heavier rock, carrying the quiet memory of ancient evaporated seas that left thick salt layers behind. It's a soft reminder that solid is sometimes only a surface impression, and that the earth has many ways of moving, some dramatic, some almost impossibly patient. And with that image resting in your mind, let's drift into another kind of transformation, one that feels gentle and almost tender. Petrified wood, where a fallen tree is slowly turned into stone, not by being simply filled, but by being replaced in detail, as mineral-rich water moves through it over time. And silica can replicate the fine structures of the wood, often ending with a specimen made mostly of silica minerals like opal, chalcedony, or quartz. The rings, the knots, the delicate textures can remain like a preserved memory, even though the original organic material has largely been lost. And trace elements can tint the stone with quiet reds, golds, greens, and warm earth tones, like nature painting slowly within the grain. To hold a piece of petrified wood in your imagination is to hold a peaceful lesson. Life can change form without vanishing, becoming a different kind of record. A bedtime story written in crystal rather than bark. And then, as your breathing stays slow, let the story move to the dark, compressed places where ancient forests became something new. Because coal begins with plant material that accumulates in wet environments like swamps or bogs, where oxygen-poor conditions slow decay and allow thick layers of peat to build up. later buried and transformed by heat and pressure over millions of years into coal with a higher proportion of carbon. There is something quietly astonishing about that sunlight once captured by leaves can be stored in the chemistry of ancient plant matter, locked away beneath sediment, and only much later released when coal is burned, as if an old day were briefly returning as warmth and flame. It's also a reminder that geology is not separate from life, because the ground can be shaped by the slow accumulation of living things, pressed into stone and kept there as a long-held memory. And in a similar way, oil has its own deep-time origin story, formed from organic material, especially microscopic marine life, that became buried in sediments and was altered over long periods under heat and pressure into hydrocarbons, later migrating and becoming trapped within rocks where it can remain until it is discovered, even without thinking about industry or machines. It can feel calming to see oil simply as another example of time's patient chemistry, the sea's smallest lives transformed into stored energy in the quiet dark. And now, let your thoughts become even lighter, like grains moving through fingers, because every grain of sand can be understood as a tiny traveler, once part of a larger rock that was gradually broken down by weathering and erosion, carried by water, wind, and ice, and sorted by long journeys until it came to rest somewhere peaceful, like a beach, a riverbank, or a desert floor. If you could look closely, you'd see that some sands are rich in quartz, and others carry fragments of different rocks, each grain shaped by where it came from and what it endured along the way. A tiny chapter of a much larger landscape worn down into softness. And in a few rare deserts, the sand itself can seem to sing, producing a low, pure note when dry, well-sorted grains avalanche together down a dune face. Their synchronized motion creating sustained sound, often described in the range of about 75 to 105 hertz, like the earth quietly humming in its sleep. The conditions can be surprisingly specific: very dry sand, grains that are well sorted and similar in size. So when it happens, it feels like stumbling upon a natural instrument tuned by wind and time. And finally, as this relaxing story continues to soften your thoughts, you can imagine shores where sand is not mostly ground rock at all, but made largely from broken shell fragments and other biological remains, built by countless small lives over long periods, so that walking there would feel like stepping across the gentle, pale leftovers of an ocean's invisible architecture. And if you picture beaches of different colors, black sands shaped by volcanic material, green sands influenced by minerals, pink sands mixed with tiny shell and coral pieces, you can let each color be a quiet hint that the earth tells its story in many palettes, each one made slowly, grain by grain, until it becomes a place you can stand and breathe and feel safe in the night. And as you keep listening to this relaxing story, you might imagine yourself strolling along those colorful shores again, where every small wave quietly rearranges grains that once came from lava, shells, and ancient rock, mixing the planet's elements into patterns that shift under changing light, as if the coastline is gently repainting itself over and over. Then, without hurrying, let your thoughts drift inland toward colder places, because glaciers also reshape the world in a way that feels calm and unstoppable, moving like slow rivers made of ice, born when snowfall gathers year after year, compressing into dense glacial ice that can slide downhill under its own weight, grinding and scraping the land as it goes over long spans. This movement can carve broad U-shaped valleys, polish rock surfaces, and carry debris for great distances, leaving behind scattered boulders, ridges of sediment, and lakes that settle into the paths the ice once occupied, so that when a glacier retreats, the landscape keeps the memory of its passing like a soft imprint. And although many glaciers move so slowly they seem perfectly still, some can surge or flow quickly enough that their motion is measurable over short periods, especially when meltwater and rainwater reach the base and increase sliding by raising water pressure beneath the ice, allowing the glacier to speed up in response to changing conditions. Studies of glacier dynamics describe how meltwater can swiftly drain to the bed and influence basal sliding, creating speed variations that can happen on short time scales, turning what looks like frozen stillness into something quietly alive. Beneath that, the ice itself can deform, because under pressure ice doesn't behave only as a brittle solid. It can also creep and flow through the slow deformation of its crystals, folding and yielding over time, which is part of how glaciers manage their steady downhill motion and their patient ability to shape valleys and mountainsides. And now, as the pace of this bedtime story stays gentle, you can imagine even smaller traces being kept by the earth, because sometimes sediment can preserve delicate patterns like raindrop impressions when drops fall onto soft mud and are quickly buried and later hardened into rock, leaving behind tiny craters that act like a quiet snapshot of weather from a vanished world. In the same softly astonishing way, fossils can sometimes preserve more than bones, because under rare conditions, soft tissues and fine structures like feathers can be preserved. And research on fossil feathers has shown that microscopic melanosomes can survive and help scientists infer aspects of original color patterns, as if a little hint of ancient sunlight remained stored in shape and chemistry. And when you zoom your mind back even farther toward the earliest chapters of life, stromatolites offer a calm kind of wonder, because they are layered structures formed by microbial mats that trapped and bound sediment in shallow waters. And some ancient stromatolite fossils are among the oldest evidence of life on Earth, while living stromatolites still exist in a few places today. And finally, letting your thoughts cool and soften like evening air, you can picture a time when the whole planet may have been far colder than anything we can experience now, because the snowball Earth hypothesis describes periods in the cryogenian when ice may have advanced to very low latitudes, potentially reaching near the equator, driven in part by feedbacks like ice reflecting sunlight and reinforcing global cooling. And now, in this quiet bedtime story, you can picture the planet during that long, pale chapter when ice may have covered much of the world, a hush of white stretching across land and sea beneath a dimmer sun. And yet, even then, life could persist in sheltered places where liquid water remained, such as beneath ice, within cracks, or near sources of geothermal warmth, waiting patiently through the cold in many explanations of snowball Earth. The ending of that deep freeze is tied to a slow buildup of carbon dioxide from ongoing volcanic activity. Because when ice covers the oceans, the usual carbon cycle processes that remove CO2 are greatly reduced, allowing the gas to accumulate in the atmosphere and strengthen greenhouse warming over long periods. As melting begins, warming can accelerate through feedbacks because darker surfaces exposed by retreating ice absorb more sunlight than bright ice, helping the planet move from a frozen state toward open water again. A dramatic shift that can feel like a rebirth written in climate and stone. And in the soft tone of this nighttime story, it can be calming to imagine volcanoes beneath the ice not as loud disasters, but as persistent, steady sources of heat and gas, quietly helping the world find its way back to flowing oceans, erosion, and the chemistry that supports life. And as the seas return in your imagination, let the story drift to the air itself, because the oxygen we breathe is linked to ancient microbes, including cyanobacteria, that used sunlight to split water during photosynthesis and released oxygen as a byproduct, slowly changing the planet's surface chemistry and atmosphere over immense spans of time. Early on, much of that oxygen was consumed by reactions with dissolved iron and other sinks, so it did not immediately build up in the air. And this is part of why banded iron formations are so important as a record of oxygen interacting with iron in ancient oceans, settling in layered deposits that later hardened into rock. This long transition, often discussed as the Great Oxidation Event, marks a turning point when atmospheric oxygen rose in a more lasting way, opening doors for new kinds of life and new kinds of chemistry across the world. And if you imagine ancient seabeds where those iron-rich layers formed, you can think of them as the planet's early breathing marks, stripes of rust and stone that hold the trace of oxygen's first great arrival, created not by anything large, but by microscopic life repeating a simple process again and again. There are also ideas and hypotheses about ancient seas looking different in color and chemistry than they do now, because before oxygen became abundant, microbial communities could have been dominated by different metabolisms and pigments, making Earth's surface feel like a stranger, more experimental world than the one we know today. And while your thoughts grow heavier and softer, you can return to the steady patience of erosion, because even the tallest mountain range is temporary on geological timescales, slowly worn down by wind, water, and gravity, until peaks can become plains, leaving only deeper roots and altered rocks as clues that great heights once stood there. The continents themselves have also gone through repeated cycles of gathering and separating, a pattern often described as the supercontinent cycle, where land masses assemble into larger supercontinents and later break apart again, reshaping oceans, climates, and the long paths of mountain building. Names used for some of these ancient configurations include Columbia, also called Nuna, Rodinia, Panosha, Gondwana, and later Pangaea, each one a reminder that the map is never final, only the current page in an ongoing story of drifting stone. And as this calming narration continues, you can keep that gentle idea close. The biggest pieces of land are only temporary arrangements, gathered and separated in a slow rhythm that changes ocean chemistry, air chemistry, currents, and climate. So that even when life was mostly microscopic, the shifting of continents still helped steer the conditions life had to adapt to. And the continents we recognize today are like scattered pages from older, larger worlds. One of the most famous of those worlds was Pangaea, assembled by about 250 million years ago into a single enormous landmass surrounded by a global ocean, connecting places that are now far apart and creating a vast interior that could be drier and more extreme. Because it lay far from the ocean's moderating influence, over time, the crust fractured, rifts widened, and the Atlantic began to open as the land broke into drifting pieces. And the matching patterns of rocks and fossils across modern oceans became quiet clues that the continents were once joined before they slowly wandered apart again. And because this is a bedtime story, you don't need to hold the details tightly. Just let the feeling of deep time wash through. The sense that Earth's map is always in motion and will keep changing long after any single era is gone. When you imagine the far future, some models suggest that in a few 100 million years, the continents could converge again into another supercontinent. Though scientists differ on whether the Pacific might close or whether other oceans might shrink instead, and the exact outcome remains uncertain, even as the process of plate motion continues. It can be soothing to picture that as a slow returning, not a catastrophe, simply the planet continuing its long habit of gathering, releasing, and gathering again, like a quiet tide in stone. And closer to the present day, you can rest your attention on single continents making their own gentle journeys, because Australia is moving northward at a pace of only a few centimeters per year, a motion tracked by modern measurements and driven by plate tectonics, so that over millions of years, it will carry Australia closer towards Southeast Asia and reshape future coastlines and mountain building zones. And in East Africa, the planet offers a different kind of slow change, because the East African Rift is an active rift system where the crust is being pulled apart, a process that, if it continues over tens of millions of years, could eventually create a new ocean basin as parts of Eastern Africa, separate from the rest of the continent. It's like watching the earliest, quietest moments of a new geography being born: earthquakes, volcanoes, stretching crust, and long lakes settling into the deepening rift. All happening so slowly that it feels like stillness, unless you know how to listen for time. And then there is Iceland, a small place on the map with a very direct connection to plate motion, because it sits astride the mid-Atlantic ridge where plates move apart, and magma rises to create new crust, bringing volcanoes, geothermal heat, and a landscape that feels like fire and ice sharing the same breath. And far out in the Pacific, the Hawaiian Islands tell another gentle tectonic story, formed as the Pacific plate moves over a long-lived hotspot, producing a chain where the youngest volcanic activity is near Hawaii, and islands and seamounts become progressively older to the northwest, like a dotted line marking motion through time. And finally, as you keep relaxing, you can hold the thought of Yellowstone as a quiet reminder that some landscapes sit above large volcanic systems with widespread hydrothermal features at the surface that reflect heat and magma at depth. And scientists describe Yellowstone as a large caldera volcanic system that has remained geologically active since its last major caldera-forming eruption about 640,000 years ago. And now, as you rest in this gentle nighttime story, let your mind stay with Yellowstone for a moment longer, not as something to fear, but as a quiet window into the Earth's deeper warmth, because scientists study it carefully, mapping and monitoring the large volcanic system beneath the park, while the surface releases heat through geysers and hot springs, like the planet taking slow, visible breaths. Yellowstone's past has included very large explosive eruptions, and USGS descriptions of caldera volcanism emphasize that these events reshape landscapes on a vast scale, even though day to day the place feels peaceful, full of forests, steam, and softly mineral-scented air. And from there, you can let the story widen to the idea of super eruptions in general, because the largest eruptions can inject enormous amounts of ash and gases high into the atmosphere, influencing climate by reducing incoming sunlight as tiny particles spread and linger, sometimes cooling the planet for a time and nudging ecosystems into difficult adjustments. One well-known example is the Mount Pinatubo eruption in 1991, which NASA describes as injecting about 15 million tons of sulfur dioxide into the stratosphere that formed aerosols, contributing to a measured drop in average global temperature of about 0.6 degrees C over the next 15 months, like a thin veil placed over the sunlight. And if you drift even farther back in time, you can picture the enormous eruption associated with Lake Toba in Indonesia around 74,000 years ago, often described as one of the largest eruptions of the Quaternary, with volume estimates commonly cited in the thousands of cubic kilometers, and a vast caldera that remains a visible scar in the landscape. Some sources discuss estimates around 28 cubic kilometers of erupted material, while others give revised dense rock equivalent volume estimates. But either way, the scale is almost hard to hold in the mind, like trying to imagine a storm made of stone and glass spreading across an entire region and beyond. And because ash and sulfate aerosols can travel widely in the upper atmosphere, major eruptions can leave traces that show up far away, in layers preserved in ice cores and sediments, quiet records of moments when the sky held more than just clouds. And then, in another gentle contrast, there are places where molten rock stays visible for long periods as lava lakes, sustained by ongoing heat and magma supply, their surfaces crusting and breaking again in a slow rhythm that can look almost like breathing, offering scientists a rare chance to observe magma behavior more directly than most volcanoes allow. And sometimes, the sky above eruptions holds its own strange light, because volcanic lightning can flash within ash plumes when particles collide, fragment, and generate electrical charging. So the plume becomes a temporary storm cloud made not from water droplets, but from ash and gas, releasing bright forks of electricity through darkness. And in places where volcanoes and glaciers meet, like parts of Iceland, eruptions beneath ice can produce rapid melting and powerful steam-driven activity, shaping distinctive volcanic landforms and reminding us, in a calm geological way, that fire and ice are not opposites here, but partners in the planet's ongoing transformation. And now, in the soft flow of this bedtime story, you can picture the ocean quietly building new land, because sometimes submarine volcanoes rise and rise from the seafloor until they finally break the surface, and a newborn island appears, steaming and dark at first, then slowly cooling under sun and wind. And in the last century, there have been several moments like this around the world, where fresh volcanic land briefly surfaced, and then either endured or was gently taken back by waves, reminding us that the planet is still writing new coastlines in real time. It's calming to imagine how quickly life tries to arrive, seabirds resting, seeds carried by wind, small plants taking hold in cracks, turning raw rock into the earliest hint of an ecosystem, as if the Earth is practicing, again and again, the same creative process that once helped shape continents. And then, as your thoughts settle, let the story drift to a different kind of hidden energy, because some deep lakes can hold large amounts of dissolved carbon dioxide in their bottom waters, kept in solution by pressure, until a disturbance triggers a sudden release, like a bottle being opened. In an event known as a limnic eruption, Lake Nyos in Cameroon is the best known example, where on August 21, 1986, a massive sea otto release formed a dense cloud that flowed into nearby valleys and caused widespread deaths. And after that tragedy, scientists began long-term monitoring and mitigation efforts, including controlled degassing systems designed to reduce the buildup of gas over time. It's a sobering fact, but in this calming narration, we can hold it gently as a reminder that even quiet water can store deep geological stories, especially in volcanic regions where gases can seep upward through the lake bed. And now, returning to land, you can think about how water reshapes rock from below as well as above. Because in areas with soluble bedrock like limestone, marble, or gypsum, rainwater and groundwater can dissolve pathways through the rock, creating karst landscapes with caves, sinkholes, sinking streams, and springs. Sinkholes can form when subterranean cavities enlarge, and the roof becomes too thin to hold, collapsing the ground above, sometimes suddenly. And although the events can look abrupt, the preparation is usually slow, water working patiently through fractures, drop by drop, for a long time before anything gives way. In those same karst regions, entire underground drainage networks can form, where streams vanish into the ground and reappear elsewhere. So the land has a hidden circulation system, like veins and arteries made of stone corridors. And deep in limestone caves, water continues its quiet craftsmanship, because dripping water can deposit calcite over time, building stalactites from ceilings and stalagmites from floors. And in some places, these formations can meet and grow into columns, as if the cave is slowly raising its own pillars. These cave deposits, called speleothems, can grow very slowly often on the scale of millimeters per year, or less, depending on conditions. And because they build layer by layer, they can preserve chemical signals that scientists use to reconstruct aspects of past climate, turning cave beauty into a natural archive of rainfall and temperature changes. And if you imagine walking through a large cave system, you can also picture the cave's own gentle weather, because airflow, humidity, and temperature differences between entrances and deeper passages can create distinct microclimates, giving the feeling that the Earth is quietly breathing through its underground rooms. And now, as you float deeper into this relaxing bedtime story, you can imagine a quiet place beneath gentle green hills, where the world's longest known cave system spreads through darkness like an unseen map. Because Mammoth Cave in Kentucky has been explored and mapped for well over 400 miles, and the known length continues to grow as new passages are discovered. The cave formed within limestone through the persistent work of water, slowly dissolving and enlarging pathways over long spans of time, until corridors, chambers, and branching roots developed into a vast network that feels almost like an underground city of stone. Inside, the air can feel cool and steady, and it's easy to imagine how silence down there seems to have its own presence, as if the earth is holding its breath while water continues its gentle shaping in hidden places. And from that quiet underground world, you can let your thoughts drift back to earthquakes, not in a sharp way, but in a slow, thoughtful way. Because very large earthquakes can slightly change Earth's rotation by shifting how mass is distributed, altering the planet's moment of inertia in a way that can change the length of day by tiny amounts measured in microseconds. NASA's Jet Propulsion Laboratory reported calculations that the 2004 magnitude 9.1 Sumatra earthquake could have shortened the length of day by about 6.8 microseconds and shifted Earth's figure axis by about 7 centimeters, changes far too small to notice in daily life, yet real enough to be modeled and discussed. And even beyond rotation, the energy from a great earthquake doesn't stay near the epicenter, because seismic waves travel through the Earth and across its surface. And after very large quakes, the whole planet can vibrate in normal modes, natural resonant oscillations, so that Earth can ring for days or even weeks like a bell struck softly in the dark. It's a strangely calming image, the world briefly becoming one connected instrument, humming with waves that scientists can record and use to learn about the planet's interior, tracing where materials are solid, where they are more fluid, and how layers are arranged far below. And if you're still listening with sleepy curiosity, you can hold another gentle truth. The energy in the largest earthquakes is immense, and the moment magnitude scale was designed to describe those huge events in a way that relates to the physical size of the rupture and the energy released, not just how strong the shaking feels at one place. Yet even with all that power, the deeper story remains patient, because far below the surface, rock does not always snap like a brittle shell. It can slowly deform, creeping under heat and pressure over long time scales, allowing folded mountains, stretched crust, and flowing mantle motion that drives plate tectonics above. And when rocks are changed by that pressure and heat without fully melting, they become metamorphic rocks, with minerals reorganized into new textures and structures that act like a record of the conditions they experienced. A kind of stone memory of burial, compression, and uplift. In that calm way, slate can be imagined as one of the quietest transformations of all fine sediments turned to rock through compaction and metamorphism, so that what once settled softly on an ancient seafloor can become a smooth, layered stone, still carrying the hush of the water it formed beneath. Even as you listen and let yourself drift toward deeper sleep, and as you keep drifting through this calming bedtime story, you can remember how slate began as soft mud and became strong through time. And now, we'll let that same gentle idea carry us into marble, because marble starts as limestone or dolostone and becomes something new when heat and pressure cause recrystallization, changing the rock into a denser, interlocking mosaic of crystals, often obscuring the original fossils and bedding that were visible in the limestone long before the transformation. It's peaceful to think that marble's smooth glow, the way it seems to hold light, is really the quiet outcome of ancient seafloors made from shells and skeletal fragments, later buried and altered until the old ocean textures softened into a more uniform, crystalline fabric. And the subtle colors people love in marble can come from different impurities and minerals present during metamorphism. So a polished surface becomes a gentle map of chemistry: soft grays, warm reds, pale greens, like a calm memory of what the stone has passed through. And then, without changing the slow pace of this nighttime story, let your thoughts move to gemstones, because crystals form when conditions are just right, with certain temperatures, pressures, and chemical ingredients meeting in rare ways deep within the earth, so that a gemstone is not only pretty, but also a record of a specific environment that once existed inside the planet. Among the most surprising examples are rubies and sapphires, which look so different yet come from the same mineral, corundum, with their colors depending on tiny trace elements inside the crystal lattice. So chromium can create the red of ruby, while iron and titanium can produce the blue of sapphire. It's a gentle lesson in how small differences at the atomic level can change how a stone carries light, turning one mineral into many colors, as if the earth is quietly experimenting with the palette of chemistry. And some gemstones are elusive, not because the crystal form is complicated, but because the ingredients rarely meet. So emerald, a variety of beryl, needs a particular combination of elements and geological settings to form, which is part of why it is less common and often naturally included with tiny internal features that mark its growth history. And then there is opal, which is unusual because it is not a typical crystal at all, and its shimmering play of color comes from the way light interacts with its internal structure, a reminder that even without crystal faces and sharp symmetry, the earth can still build organized beauty from silica and water over time. And now, as this relaxing story turns its gaze outward, you can imagine a different kind of stone messenger arriving from space, because meteorites can preserve material from the earliest solar system. And within some primitive meteorites, scientists have found presolar grains, tiny bits of stardust that formed in stellar outflows before the sun and the planets existed. These grains are identified by their unusual isotopic signatures, which differ greatly from typical solar system materials, like a chemical accent that reveals they were shaped by nuclear processes in ancient stars, then survived long journeys through space before becoming trapped in meteorites. To hold that idea gently without effort is to realize that geology is not only the story of Earth, but also a quiet continuation of older stories, because some of the matter in rocks has been recycled through stars, carried through darkness, and finally gathered into the ground beneath our feet, waiting for you to listen as you fall asleep. And now, as this bedtime story continues in a slow, soothing rhythm, let your thoughts lift gently from Earth for a moment and rest on the moon, because the rocks astronauts brought back during the Apollo missions became more than souvenirs from another world. They became clues about our own beginning, and one of the strongest ideas they helped support is the giant impact hypothesis, where the moon formed from debris after a collision between the young Earth and a planet-sized body, with lunar and terrestrial rocks showing remarkably similar stable isotope ratios, especially in oxygen, hinting at a shared origin and extensive mixing during formation. It can feel calming to imagine those samples as small, quiet time capsules, holding evidence from an era so early that Earth's own surface record has been repeatedly erased by tectonics, weather, and recycling, while the moon's airless surface preserves scars and stories for far longer. And as you let that idea settle, you can drift back down to Earth and picture something even smaller than a pebble carrying an even older message, because among the oldest minerals ever studied on our planet are ancient zircons from places like the Jack Hills region of Western Australia, tiny crystals that can be dated to more than 4 billion years old using uranium lead methods, because zircon incorporates uranium when it forms, and uranium decays to lead over time. These zircons are resilient enough to survive long histories of erosion and metamorphism, and some analyses of their chemistry, including oxygen isotope evidence, have been discussed as suggesting that liquid water may have existed at Earth's surface very early, implying the planet cooled enough for surface water sooner than older, molten for ages pictures once assumed. In this relaxing story, you don't have to hold the numbers tightly, just the feeling that a crystal smaller than a grain of sand can outlast whole continents and still keep a quiet hint of the world's first rains. And now, staying with the theme of vast change, you can imagine times when the continents themselves were covered by enormous fields of basalt, because flood basalt provinces are created by repeated outpourings of lava that can cover huge areas and build thick plateaus over long spans, leaving behind dark stepped landscapes like those associated with places such as the Deccan Traps and the Siberian Traps. These events could release large amounts of gases, influencing climate and ecosystems, and the Siberian Traps in particular are widely discussed as occurring around the Permian-Triassic boundary and being linked with the most severe mass extinction in the geologic record. Even that thought can be held gently here, not as alarm, but as part of the planet's long rhythm, where endings make space for new beginnings, and the Earth keeps reshaping life's possibilities through chemistry, climate, and time. And when you think of ash from eruptions, you can picture it not only as a drifting cloud, but also as a thin layer preserved in sediments. Because volcanic ash beds can be matched and dated using their chemical and mineral signatures, helping build timelines of past events, while also, in some places, contributing minerals that enrich soils over time. And finally, as your mind grows heavier and calmer, you can return to oceans being born, because the Atlantic itself began as a rift that opened as continents separated during the breakup of a supercontinent. And today, the Mid-Atlantic Ridge still marks an active zone where new oceanic crust forms as plates move apart, a slow continuation of the same process that once started as a crack in connected land, and now, still moving gently through this nighttime story. You can imagine an ocean that began as a narrow opening in rock and slowly widened into a whole world of water, because the Atlantic continues to grow from its center, where the Mid-Atlantic Ridge runs like a long hidden mountain chain beneath the waves, and new oceanic crust forms as magma rises, cools, and spreads outward on both sides. As that fresh basalt moves away from the ridge, the continents on either side drift with it, so the ocean floor behaves like a slow conveyor belt, steady and symmetrical, carrying the quiet work of seafloor spreading year after year. And in those cooling lavas, tiny magnetic minerals align with Earth's magnetic field, recording its direction, so that the seafloor preserves alternating bands of magnetic polarity. And USGS describes how the close match between observed magnetic stripes and the known history of magnetic reversals provided a crucial argument supporting seafloor spreading and plate tectonics. It's calming to realize that the ocean floor keeps such a neat memory. Lines written without ink, only magnetism and time, while the spreading itself remains almost imperceptible in a human lifetime, yet unstoppable across ages. And along these ridges, another kind of quiet wonder appears, because hydrothermal vents form where seawater circulates into fractured crust, heats up near magma, and returns to the seafloor carrying dissolved minerals. And when that superheated fluid meets cold seawater, it can precipitate dark particles, producing the smoky plumes that gave black smokers their name. Some black smoker fluids can reach temperatures around 350 degrees C, or even higher near the vent openings, and the chimneys can grow as minerals accumulate, then collapse and rebuild, like slow, underwater architecture, always under construction. And around these vents, life gathers in a way that once seemed impossible, because ecosystems can thrive without sunlight, relying instead on chemosynthesis, where microbes use chemical energy from compounds like hydrogen sulfide to build food, forming the base of a whole community that can include tube worms, clams, and other animals adapted to that extreme setting. The discovery of hydrothermal vents in the late 1970s reshaped biology by showing that energy, water, and chemistry can support rich life even in deep darkness, like a hidden garden powered by Earth's internal heat. And now, as you stay with this calming narration, you can return to the planet's magnetic field itself, because the geomagnetic field has reversed many times in Earth's history, and those reversals are recorded in rocks, especially in oceanic crust, where the magnetic minerals lock in the field direction at the time the lava cooled. During a reversal, compasses would gradually become less reliable as the field weakens and reorganizes. But the process unfolds over long spans, and the geological record shows that life has persisted through past reversals, making them part of the planet's natural variability rather than a sudden ending. And even without a full reversal, the magnetic poles wander, and recent measurements show the North Magnetic Pole has been moving away from the Canadian Arctic towards Siberia, with speeds over recent decades often described in the tens of kilometers per year, sometimes reaching around 50 to 60 km per year during its faster phases. And as you continue to float through this gentle sleep story, you can hold one simple distinction in your mind. Geographic north stays fixed to Earth's spin axis, while magnetic north wanders because it is shaped by shifting flows in the liquid outer core. And that wandering is a quiet reminder that the invisible shield around our planet is alive and changing. The magnetic field that guides compasses and leaves its imprint in cooling rocks is, in a sense, the surface trace of deep motion we can't see directly. The slow stirring of metal far beneath the crust. And now, in the same calm way, let your imagination rise to the moon again, because many discussions of Earth's long-term stability note that the moon influences Earth's axial tilt, helping keep the obliquity within a comparatively narrow range over long spans. And models have suggested that without the moon, Earth's tilt could explore much wider, potentially chaotic ranges that would strongly affect climate patterns. It's gentle to picture that as a kind of quiet partnership, an orbiting companion that helps smooth the rhythm of seasons, even while other research debates the exact degree of stabilization and how it changes over billions of years. And closer to the shorelines where people actually live, you can feel the moon's pull through tides, the daily rise and fall of ocean water that, over time, moves sediment, shapes estuaries, and subtly rewrites coastlines grain by grain, like a slow breathing that never forgets its rhythm. And in some places, that tidal range can be dramatic, creating broad intertidal zones that alternate between sea and land, supporting rich coastal habitats and constantly rearranging the border where water meets stone. Then, still staying in the soft tone of this bedtime story, you can drift toward coral reefs, because reefs are not only living communities, but also geological structures built from calcium carbonate skeletons over countless generations, stacking upward and outward as old coral becomes foundation for new growth. The Great Barrier Reef, for example, extends for roughly 23 kilometers and can be photographed from space, a vast construction made from tiny builders repeating their quiet work over long time. And as sea levels rise and fall across eras, reefs can grow upward or shift their active zones, leaving behind fossil reefs that later appear far from the ocean. Reminders that what is seabed in one age can become land in another. And finally, letting your thoughts drift like fine powder in air, You can imagine deserts feeding distant forests, because satellite-based studies have estimated that phosphorus carried in Saharan dust delivers about 22,000 tons per year to the Amazon basin, helping replenish nutrients that heavy rains can wash away, linking faraway landscapes through wind and time. It's a quiet kind of connection, erosion becoming flight, flight becoming nourishment, and a grain of rock leaving one place to support life in another. As you rest and let the story carry you toward deeper sleep, as you settle deeper into this relaxing bedtime story, you can imagine those ancient impacts as a quiet rain of metal from space, scattering debris and leaving behind traces that later became part of the upper crust, so that a vein of gold or a fleck of platinum can feel like a small inheritance from events far older than any human story. A gentle reminder that earthly beauty sometimes begins in distant cosmic history. And when you look at the land with that soft perspective, it becomes easier to accept that many impact craters do not stay dramatic for long, because over immense time, wind and water wear down rims, sediments slowly fill the bowl, and tectonic motion can blur the shape until the scar becomes hard to notice. Even though the rocks can still hold subtle signs of shock and melting that point back to the moment of collision, and in some cases, those hidden circles are found not by sight, but by careful measurements that reveal faint patterns in the ground, as if the planet covered its old wounds with new layers and then continued on, calm and unhurried. And while impacts can feel sudden in imagination, their influence can echo through life's history in ways that unfold over long stretches. Because when the environment changes quickly, some lineages struggle while others find new openings, and the living world slowly rearranges itself, turning disruption into a different balance. One of the most famous examples is the impact about 66 million years ago at Chicxulub, linked with a mass extinction that ended the age of non-avian dinosaurs. And although the crater itself is buried, its shape and evidence remain beneath younger rock, like a sealed page in the planet's diary. And even now, when the night feels still, the Earth continues receiving a gentle fall of space material, tiny grains drifting into the atmosphere and settling quietly onto oceans and land. A soft reminder that the planet is still in contact with the wider solar system, still collecting small additions while it endlessly reshapes what it already has. And as this nighttime story keeps flowing, you can let all the pieces we've visited, mountains rising, oceans spreading, ice carving valleys, caves growing drip by drip, fossils keeping whispers of ancient storms, and stardust hiding inside stone, rest together in your mind as one connected tale. Because geology is the slow, calm language that links them all, showing how fire, water, pressure, and time keep rewriting the surface of the world in a steady rhythm, and how every pebble and cliff is part of that ongoing transformation, quietly waiting while you fall asleep and drift toward deep sleep. Even as everything grows quiet for this bedtime story, you can remember that the feeling of solid ground is only a gentle impression, because the Earth is always moving in ways too slow to notice, endlessly patient as it forms, breaks, and reforms its thin outer skin. And if you listen with your imagination, can almost sense a long, low memory in the stone, a calming narration written without words, steady and unhurried. Right now, while you rest, the planet turns beneath distant stars, and the minerals in the ground and in your own body trace back to ancient processes that began long before any human day. While far below the surface, heat keeps rock cycling in slow motion, guiding continents as they drift like quiet shadows across a deep foundation. Geology is a relaxing story because it shows that change doesn't need to be loud. Most of it arrives as a whisper, mountains lifting so gradually they feel timeless, oceans widening so slowly they seem fixed, and yet everything is gently on its way somewhere, shaped by pressure, building in one place and easing in another, where new stone begins its long transformation. And above it all, wind and water keep working, soft and persistent, grinding rock into dust, carrying that dust across great distances, letting it settle where it can become soil again, where it can quietly support life, so that what once felt like unbreakable cliffs can eventually become the finest grains. And those grains can someday be pressed back into stone, beginning another cycle. You might think of the textures you've known in the world, the crisp sound of pebbles underfoot, the cool firmness of a rock face, the gentle warmth of sand, and how each one is a small chapter made from minerals shaped by time and touch, held together by the same deep processes we've been drifting through tonight. And it can feel soothing to realize that the earth is not only alive at the surface, but alive within itself, turning memory into matter, turning silence into form, always reshaping, always renewing, without hurry and without end. As you drift toward deep sleep, let that idea sink softly, like rain disappearing into soil. Imagine the planet's slow pulse beneath you, ancient and steady, and let it ease your thoughts and slow your breathing until your body feels heavy and safe. You are part of this nighttime story too, a brief, gentle moment within a much larger unfolding, and you don't have to hold anything tightly now. Just rest. If you enjoy these quiet journeys on Sleepy Story Facts, you can softly support the channel by liking, subscribing, or leaving a kind comment, so other sleepy listeners can find their way here as well. For now, simply breathe. Let your eyelids grow warm and heavy, and let the earth cradle your thoughts, still patient, still quietly changing. As you slip into sleep, good night.